Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And this is part of a little mini-series within that larger playlist called Split Plot Design. We're on part 5 of 10, and here we're going to look at the best linear unbiased estimate in this setting. Now, the model we're going to look at is called Split Plot Design Randomized Complete Block. Now, I'd encourage you to watch parts 1 and 2 for more detail on that, but it has to do with the first randomization that occurs within the split plot design. So here's the model, right? And if you look at that, that's a randomized complete block design, and then this is the second randomization within each of the whole plots. Here we're going to move the error term into this. And in matrix form, you can let it be mu times 1, and then the first factor, alpha, the block effect, second factor, the interaction between the two factors, and the error term. Now this can generically be represented like this: x times beta hat, this vector of unknown parameters, which deal with, it's all of these in one, and the error term. And this error term is multivariate normal mean 0 and covariance matrix sigma squared v, where sigma squared is this. And what we're going to look at is finding the blues of an estimable function for these beta parameters. Now, everything we've done up until this point, the covariance matrix has been sigma squared I. And then, the Gauss-Markov theorem tells us that it's a blue. But there's also another way that you can tell that the ordinary least squares regression are the best linear unbiased estimates, and by this author here. And I'm not going to pronounce it because I always get knocked for mispronouncing the name. But in 1962, they proved that if you take v times x, so this is v, and that's x, the column space of v times x is a subspace of the column space of x, then the ordinary least squares estimator of x beta star is a blue for this. And so that is the least squares estimate, x beta, where this is the least squares estimate. And it has to equal m times y, where m is the perpendicular projection matrix onto that column space of x. We know that it is a blue for this. And now, one quick note: before, we've always had an I here, and look at this. I times x is just x, and the column space of x is clearly a subset or subspace of column space of x. So, by this theorem in this article, it's a blue, right? But when it's a generic covariance matrix, not always obvious. So let's prove that for the split plot model, randomized complete block model, we're going to show that the column space of v times x is a subspace of the column space of x. Now, from part 1, we showed that sigma squared v was equal to this, where this is sigma squared, and v was this matrix here, where rho, the correlation between the error terms, was this. So it's sigma w squared. So that's the whole plot variance. And if we go back up here, I didn't write it specifically, but that's the whole plot, and then this is the variance. So it's the correlation. And this is the perpendicular projection matrix on if we were to model the whole plot. So this would be that column space, and it's equivalent to the interaction between alpha and beta. So if we look at Vx, so this is V and this was x. So if you take x times I, you get x back. Now I didn't expand the columns here, but it's that. So really the tricky part, and this is clearly within the column space of x, right? It's just a multiple times it. So really the tricky part is this times x. So now when we multiply this times the first 3, this MW is actually, these 3 columns spaces are within this called the interaction space, right? So pre-multiplying each of these by MW, you just get them back. And so that's what this is. So this is this one. That one is this one, right? MW times X alpha, you just get X alpha back. So this times that is this. So the tricky ones are these two column spaces. So that times this. Now, in part 3, we showed that this was equal to that. And then in part 3, we showed that this was equal to this. And the reason that we do that is now we have X back. So this is X, and it's on, and I'm going to say it's on the left side, so it's pre-multiplied by this, right? So that says that we can, right, that's a constant which can be put in here. That's a constant put in here. These are constants, can put in identity matrix, same here and here. So then we can create a Q, and I'm skipping that step. So we take X times this matrix Q, and we get this back. And the reason we do that is that we can left factor out an X, and then this is clearly part of this. It's a something times the columns of X, which is how you define the column space of X. So it's clearly a subspace of the column space of X, and then it's finished. So the split plot models are part of this, are blues. So if we take the ordinary least squares estimates for the beta parameters, we can create blues. So because of this result, the least squares estimable functions are blues, and that's very exciting because it makes the job easier to estimate these. So for split plot, randomized complete block design, and really this is my notation. I don't think other statisticians use it much, but I like to put this because that's the first type of randomization in the split plot model. So the estimable function, lambda transpose beta star, is estimated with the least squares estimate here. So we plug in the least squares estimator, and so this is a blue. It's the best linear unbiased estimator for this estimable function. So let's look at it in a little more detail. So lambda transpose beta star tilde. So that's the least squares estimate. Now since we know it's estimable, this lambda has to be part of the row space, right? But then we know that this, because it's the least squares estimator, is equal to my, where beta star tilde is the least squares estimate of beta star. So that means, so coming down here, so then M, the structure of that perpendicular projection matrix, which we proved in part 3, is this. Then when you multiply the y in, you get these mean vectors, which we also proved in part 3. And then, rho times it. And that's it. That's the structure of the blue, the best linear unbiased estimate for this estimable function. So let's look at it in a specific detail. So let's say we want to estimate the mean response at the ijk level, which is this. And then this can be, we can put this into an estimable form. So it's estimated with blue this. Okay, so we put in the least squares estimate for beta, which then since it's estimable, well, we don't know it's estimable, but it is. So that means we can find a rho times rho transpose times X. So we can create something that's part of the row space, and I'll show you that in a second, which is this, right? This is my. Now, rho is this, so it's all zeros except for 1, 1 in this position. And then what that does is it picks off the correct parameters. But so we take this here and bring it down. Remember, this right here created those mean vectors, but this it is all zeros but 1, 1. So it picks off just that component, and you get the mean of I dot k dot j dot, and then minus the the grand mean, and that's it. So this is the blue for this mean response. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video, subscribe so you don't miss the next one. Thanks, bye.